London, one of the most influential cities in the world, a global financial hub, a center of culture, and a key gateway for international travel. Every day, millions of commuters, tourists, and business professionals move through the city. But transportation has always been a challenge. The existing underground and rail networks were operating beyond capacity. Major lines, such as the Central and Jubilee lines, suffered from severe overcrowding, while east-west travel remained slow and inefficient. Long-distance commuters used to travel about 3 hours a day. A global city like London needed a faster, more efficient alternative. Then in 2022, a new railway emerged to transform London's transport system, the Elizabeth Line. From Royal Oak in the west of London to Plumstead in the east, a total of 42 kilometers of new tunnels were constructed, connecting 41 stations. At that time, there was a reason that desperately needed a transportation revolution from the Elizabeth Line. And that was none other than Canary Wharf in the Docklands. The key technology that allowed the Elizabeth Line to pass through Canary Wharf was the TBM, the tunnel boring machine. There are various types of TBMs used for excavation, but the equipment used as Crossrail station was the Earth Pressure Balance TBM. This type was chosen for excavating the Canary Wharf area, which consists of soft and mixed ground, as it ensures ground stability during tunneling process. TBMs are typically built to lengths of 16 to 100 meters and in special cases even over 120 meters. As the length suggests, TBMs are specialized for straight sections capable of excavating long, uninterrupted paths in a single drive. However, this strength becomes a limitation in highly curved sections. Navigating tight bends with such a long machine is no easy task. In these areas, sprayed concrete lining (SCL) is required. Another exception is that TBMs, while specialized for straight sections, are not completely incapable of passing through curved sections. The ability of a TBM to navigate a curve depends on the radius of the curve and the size of the TBM. While TBMs are equipped with mechanisms that allow the machine to rotate in the direction of the curve, they can only pass through the curves with a minimum radius of 150 to 200 meters. In the case of London's Crossrail project, some TBMs were able to pass through the curved sections as a minimum radius of 200 meters was available, allowing the work to proceed. Once the TBM reached the station, lifting brackets and cranes were used to move it across the pre-constructed station box to the opposite side. This is how the station tunnels were excavated. Next comes the story of station's construction. Canary Wharf Station had to build not on land but over water due to the distribution of the buildings in this area. As a result, it was constructed within the waters of the North Dock of the West India Docks, designed by Fosters and Partners in collaboration with Grimshaw, the firm responsible for the overall design of the Elizabeth Line. Both firms focus on providing a comfortable environment for users, a quality clearly reflected in the design of the Canary Wharf Crossrail station. At that stage, connectivity was also a key consideration. On the west side of the station at ground level, level 0, the Adams Plaza Bridge serves as a connection between 1 Canada Square and Crossrail Place. Meanwhile, the bridge on the first basement level links the popular area with Canary Wharf. Inside the station, the tone of the finishes and the layout of openings on each level were carefully designed to create an intuitive flow for passengers, ensuring seamless spatial connections. With the design now complete, the next step was to bring it to life through construction. However, during the construction process, unexpected challenges arose, leading to adjustment in the original design. This building was originally designed to construct a station box over 300 meters long by reclaiming North Dock. However, considering cost and site conditions, we shortened the station box to 260 meters and chose to use a cofferdam instead of land reclamation. Next, a geotechnical investigation was conducted to prepare for construction beneath the water. Based on the findings, site-appropriate construction methods were selected, including cofferdams, tie roads, anchor, and tubular piles. With the design and construction plans in place, the project now moved into full-scale construction. We need to construct the building both above and below this dock you see here. By constructing a cofferdam here, water is temporarily blocked to create a dry working space for construction. Since water tightness was crucial, we used 18-meter long tubular piles and installed a total of 310 of them. Before driving the piles into the ground, we used augering method for pre-boring, followed by hydraulic pressing to install them. We first drive 2 or 3 piles into the ground with high precision. Then, the crane lifts the silent piler main unit and mounts it onto the installed piles. From this point, the silent piler switches to self-propelled mode and continues the work by moving on its own. Since the piles need to be installed in a U-shape, the piler has to turn corners. Even then, this machine automatically changes direction and moves on its own. As the piler drives the piles, interlock connections for water tightness are made immediately behind it. These connections link each pile to prevent water from entering the cofferdam. Additionally, to reinforce the watertight performance of the interlock joints, waterproof synthetic fiber sheets called geotextiles were inserted, and cement-based waterproof grout was injected into the gaps, completing a fully watertight cofferdam. This cofferdam had to withstand long-term loads as it was also used as permanent structure. Therefore, additional reinforced concrete piles were installed inside each hollow steel pipe pile to provide internal reinforcement. After driving the steel pipe piles to a depth of 18 meters, dry drilling was performed to install the RC piles, which were then inserted as concrete-filled piles down to 36 meters below the water surface. Since the internal reinforcement alone was insufficient to resist external lateral loads and water pressure, ankle piles were required. These piles, having the same specifications as the steel tubular piles, were additionally installed outside the cofferdam. At this time, the east and west ankle piles could not be arranged in a straight line because they were installed to avoid the TBM's path. And also, the anchor piles were reinforced with deep RC piles inside them. A total of 160 ankle piles were driven in at intervals of 2.92 meters. The installed ankle piles were connected to the cofferdam steel tubular piles with tie rods. This was to ensure that the cofferdam steel piles remained stable and did not tilt during construction. Considering when the water was pumped out, hydraulic jacks were used to apply a force of about 100 kN per meter to the tight walls, anticipating inward movement. As a result, initially, the walls were pushed outward, opposite to the excavation direction. But later, during dock dewatering, they moved toward the excavation direction. It might seem that the north, east, and west walls were completed as planned, but in reality, the cofferdam was extended beyond the main boundary of the station on the west side. Historically, this area was a passage used by ships, and during redevelopment, it was intentionally left open to accommodate future transportation and infrastructure needs. When Canal River Station was eventually built on this site, that space was repurposed as a passage, becoming a crucial pedestrian route connecting the Elizabeth Line's Canal River Station with the existing Jubilee Line Canal River Station. This connection was made possible through the construction of the Adams Plaza Bridge, with the central area becoming known as Adams Plaza. To carry out construction in this extended area, a dry working space had to be secured there as well. However, there wasn't enough space in that area to install anchor piles. As a result, a tight back retaining wall system couldn't be applied to the gigantubulal piles. As an alternative, we installed a berm cantilever sheet pile wall. This structure enhances resistance to water pressure by forming a berm, an embankment of soil or gravel behind the sheet piles. It is one of the techniques used in underwater berm construction, and in this case, materials were placed using both dumping from bridges and pipe-based installation methods. In this way, the north, east, and west walls were completed. The south wall was formed using the existing structure that had been part of the original dock, thereby completing all four sides. This is what Canary Wharf looked like in 1940s. This area was originally land. To create a dock, the ground was artificially excavated and water from the River Thames was brought in. Later, as the area was developed, the dock transformed into a global financial hub, with tall buildings being constructed. To support that transformation, land that was stronger and wider than the original site was required. To expand the site, the dock infill method was applied. Depending on the required expansion range, the outer boundary is formed with sheet piles or concrete walls, and the inside is filled with soil to create a new site. Since a high-rise building was scheduled to be built on top of this reclaimed land, a slurry wall was constructed to structurally reinforce the edges of the site. The slurry wall is a construction method that forms a deep and solid underground concrete wall. First, the ground is excavated. Then, slurry is filled to prevent soil collapse. A river cage is inserted inside, and concrete is poured to complete the wall. Through this method, both the water blocking function and structural stability of the site's outer perimeter were secured. Since this slurry wall was located on the south side, there was no space to install additional anchor piles or tie rods, so the wall was used as it was in the construction. Now, it's time to pump out the water trapped inside the cofferdam. After dewatering created a dry environment, it was time to lower the equipment underground for the top-down construction. A sheet pile ramp was installed, allowing equipment to be moved toward the east in the direction of the Great Wharf Road Bridge. In addition to the existing southern wall of the previous building, which served as a barrier for dewatering, an additional southern wall, a second pile wall, was required for the construction of Canary Wharf Station. First, pre-drilling is carried out using a continuous flight auger. Once the excavation is complete, second piles are installed. Unreinforced concrete soft piles are installed first to act as an initial earth retaining wall, followed by reinforced concrete hard piles between them to ensure structural strength. This second pile wall, constructed in this manner, supports the ground with its own rigidity, thereby securing structural stability. Now begins the full-scale implementation of the top-down construction method. Plunge columns are driven into the locations where the building's reinforced concrete columns will eventually be placed. These plunge columns temporarily support the load of the upper slabs during the top-down process. Due to the nature of the method, where slabs are constructed from the top-down downward while excavation process below, immediate structural support is required during each stage, and the plunge columns serve this critical role. A total of 30 plunge columns were installed on site, driven down to a depth of 40 meters below the surface along the building's center lines. The columns were not aligned in a perfectly straight line. At future more hole locations, 2 columns were placed side by side at 3-meter intervals. Once excavation is completed down to the lowest level and the permanent columns are installed, the structural role of these plunge columns is partially transferred. They are then integrated with the superstructure and used as part of the permanent structural system. Let's take a closer look at the construction process, starting from the sublevel 3, which is closest to drain dock bed. First, The ground is excavated to a depth of approximately 2 meters. Then, temporary supports are installed in intervals of about 1.5 meters to support the formwork that will be placed afterward. In areas designated for mall halls, spaces reserved for the vertical transportation of materials and workers, as well as for future escalators and elevators, plunge columns are interrupted and cannot connect directly to the beams. To address this issue, temporary columns were installed within these areas to provide additional structural support. In addition, reinforcement beams were constructed around the mall hall openings between the piles and the plunge columns to enhance stability. On top of the formwork, reinforcement bars for the beams are placed first, followed by the reinforcement for the slab. One important point to note is that reinforcement and concrete pouring are carried out except the mall hall areas. At the sub-level 3, a total of 23 mall halls were installed. This includes 4 ventilation shafts located at each end of the floor, 1 stair core, 1 elevator core, 1 escalator opening, and several additional openings for escalators and elevators, providing access to the retail area. For the concrete placement of the slab, the work was divided into 9 separate sections organized around the mall halls. Due to the nature of the top-down construction method, the upper slabs are built first, followed by the lower slabs. At this stage, it was impossible for the plunge columns alone to support the upper slabs, which span up to 30 meters in width. Therefore, additional support was required to provide basic connections between the plunge columns. For this purpose, the existing second pile wire and sheet pile wire on either side were utilized. During the construction of the sub-level 3 slab, the second pile wire was located below the slab level, naturally providing support at one edge of the slab. Support on the opposite edge was provided by the sheet pile wire. Therefore, the south side supported the slab by placing it on top of the second pile wire. However, on the east, west, and north sides, the kick-in piles protruded 9 meters higher than the slab of the sub-level 3 floor, so they could not be supported in the same way as the second piles. At this time, the slab was supported by connecting the sub-level 3 slab and the kick-in piles through the method of slab embedded into wall socket. Grooves were curved into the existing kick-in piles to connect the internal rebar with the rebar of the sub-level 3 slab. In this way, the kick-in piles were able to support the load of the sub-level 3 slab. Thus, a structure was created where both ends of the slab are supported by the kick-in piles and second piles, and the center is supported by the plunge column. The excavation for sub-level 4 was carried out simultaneously. Excavation began beneath the formwork through the mole holes. Through the mole holes, workers and materials needed for excavation were moved downward. After the excavation for sub-level 4 was completed, the process of constructing the sub-level 4 slab began, just like the sub-level 3 slab. There were a total of 21 mole holes in sub-level 4. Rebar was placed except in those areas, and to support the slab edges, second piles were connected on the south side and the kick-in piles on the north side. Since both the second piles and the kick-in piles protruded above the slab, a slab-embedded connection method was used to connect the slab rebar to the piles. After that, concrete was poured into the formwork. After the sub-level 4 slab was completed, excavation was carried out for the sub-level 6 construction. Likewise, excavation and slab construction were carried out, while column and wire reinforcement work continued on sub-level 4 and 3 to effectively shorten the construction period. It is important to note that sub-level 6 was constructed before sub-level 5. The subway runs at the lowest level of the station, sub-level 6, so the TBM also had to pass through sub-level 6. The diameter of the TBM used in the Crossrail project was 7.1 meters. If sub-level 5 was constructed first, the TBM would either have to break through that level while passing or might not be able to enter at all. Therefore, instead of building sub-level 5 first, sub-level 6 was constructed to secure space for the TBM. In fact, The floor-to-floor height difference between the sublevel 4 slab and sublevel 6 slab is 10.1 meters, and by removing sublevel 5 in between, a vertical clearance sufficient for the 7-meter TBM to pass was secured. In addition, unlike other floors, the slab at sublevel 6, which is the deepest part of the Canary Wharf station, has slopes at both ends. Since earth pressure and water pressure act horizontally in the underground, the slab was sloped to disperse these forces. After the TBM passed and the construction of sublevel 5 was completed, all the slabs of our station were constructed. In the middle of this process, to form the wall, SCL, which means concrete lined, was applied by spraying concrete along the excavation surface. Simply put, it is a method of forming a wall by installing a reinforcement mesh on the excavation surface and then spraying concrete. This is a cross-section of the building, and let's look at the slab. We can find out that the thickness varies depending on the section. The slab on the east side of sublevel 4 is relatively thinner. This is related to the TBM entry. During TBM operation, cumulative error can occur. The error can reach several tens to hundreds of millimeters. Considering that, the slab thickness was reduced to secure a wider passage for the TBM. Also, the slabs at both ends of sublevel 3 are lower than the center. This is to secure a higher floor height, as the space behind the escalators on both sides houses the MEP plant. In this area, air handling units, FCUS, electrical panels, pumps, and tanks are installed. To support the weight of the equipment and for soundproofing design, a thick slab was applied. In the center of sublevel 2, there are retail shops, and at both ends, there are spaces to manage them. Due to the high live load acting on the shops, precast beams and planks were used for reinforcement. Columns were installed and precast beams were placed between them, followed by precast planks installed on the top of the beams. The slab on the east side of level 0 was made thicker. At this location, there is a bridge for vehicle traffic, and the dynamic impact load from that acts much greater than the static load. In addition, since the vehicle load is directly transferred to the lower slab, the lower slab must have higher resistance to bending, shear, and deflection than a normal slab. At the location of the vehicle traffic bridge, which is the reason why the level 0 slab was made thicker, there originally existed the Great Wharf Road Bridge. This was the lifting bridge with a length of 68 meter, width of 24 meter, and a height of 10 meter, and it could be lifted up to a maximum of 18 meter to allow ship passage. During the construction process of the Crossrail station box, the bridge was actually lifted to its maximum height of 18 meter to facilitate construction. However, during the construction of level 0, it overlapped with the existing bridge, making demolition unavoidable. Accordingly, the existing bridge was completely demolished, and later, a new lifting bridge called the New Upper Bank Street Lifting Bridge was installed. This bridge, which allows vehicle traffic, connects the north wall of Canary Wharf Station to North Quay, and it is 26 meter wide and 22 meter long. We have covered the exterior and interior of the building, as well as the bridge. Now, what remains is the roof located at the top of our station. The most prominent architectural feature of Canary Wharf Station is its roof structure and rooftop garden. The Crossrail Place roof at Canary Wharf spans 310 meters in length, with each end cantilevering 13 meters over the surface of the north dock. The roof construction of Canary Wharf Station involved the use of 1418 glue lamps and 564 steel connectors. This roof is constructed in a diagrid form. The term diagrid is a combination of diagonal and grid, describing a structural system that maximizes stability and load distribution through a network of diagonal lattice members. By distributing loads diagonally, the diagram system can support the structure without relying on conventional vertical columns, enabling more open and flexible architectural designs. The roof structure was designed using algorithm-based parametric modeling, making the lattice, beams, and connectors all asymmetrical and non-repetitive. Each component was prefabricated and assembled on site. Timber beams in ETFE were connected at knots with air pipes in between to control air volume according to wind pressure, keeping the ETFE shape consistent. Temporary steel supports were used during construction to support the roof. A rooftop garden was created below the roof, and to support the soil, the slab was made thicker than on other floors, resulting in a higher load. The building's east end could not have columns due to the new upper bank stair-lifting bridge, so steel with higher tensile strength was used. This steel is more flexible than concrete, and adding soil and trees after the roof construction could cause it to bend under extra load. To prevent this deflection, the garden load was simulated, and a water tank was installed on top to apply a pre-stress of 300 tons. Through this, it was possible to respond to deflection even when soil and trees were added. The construction of Canary Wharf Station has now been completed. As part of the Elizabeth Line, Europe's largest infrastructure project, Canary Wharf Crossrail Station faced various issues including financial, contractual, and construction errors, causing delays. It was completed 13 years after groundbreaking. During this period, construction costs overran from £14.7 billion to £18.8 billion. Overcoming this, Canary Wharf Station has been recognized for its contributions to London's infrastructure, innovative design, and urban regeneration, earning several awards and steadily solidifying its position.